Thank you for being here.
Okay, so let's start it. Thanks a lot for the introduction. So this talk is about Docker patterns. So there are two parts, about Docker, of course, and patterns which we can apply to the Docker world. I have a small road trip for you, what you can expect for the next 45 minutes. First, I give some sort of context. What is Docker? Hopefully I haven't explained too much there. What do I understand under patterns? And then we will touch several areas which might be useful for you if you are developing against Docker. Okay, let's start. First of all, Docker. So my usual first question is always, who has never heard about Docker? That's very good. You never heard? Okay. But nevertheless, the other question is, of course, who has used Docker already? Robert? Okay, so I only go briefly now to the concept. I have only this single slide about Docker. What is Docker? What is different from Docker in contrast to other virtual machines? So Docker itself is a virtualization technology. And it differs to a classical virtual machine approach that it doesn't simulate the hardware via its hypervisor, but it simply does build up some sort of cage, some sort of isolation boundaries, so that you can have a much more higher density of so-called containers running on an operating system. One of the unique features of Docker is, of course, that all these containers running on the same system share the kernel. And what Docker does simply is it builds up some isolation boundaries around a process. This kind of technology is not new. It happens to be used since many, many years, 10 years or even much longer. The thing which Docker brought onto the table was simply a very great user experience. So they had some sort of CLI system, a Docker daemon. The communication is very easy to use, so you can set up Docker within minutes. And also some sort of extras like a layered file system and so forth. So as said, Docker is a container, OS level virtualization technology. But these days, Docker is not alone anymore. So you have Docker in the center. But around this, a lot of other tools and frameworks has been created. And one of the reasons that Docker itself is always constrained to a single host. And of course, if you want to make a lot of many containers and want to scale out and want to distribute it over a whole fleet of nodes, then you need some sort of orchestration software. And there, in the orchestration world, there are much more possibilities to choose from. So you see Kubernetes is an orchestration platform. You see Docker Swarm Mode. You have Mesos is also something which plays in this area. And what I want to say is that you have now a whole slew of technologies. They all have their own configuration things. They all have all the things how they do stuff. But if you look closer, you will see some sort of common usage pattern among all of these. And I hope that I can show you today some of them. So this was Docker. The other part which I want to tell briefly is about design patterns. So design patterns is a very old concept. And first of all, what I understand under design pattern? So a design pattern is a repeatable solution for a software problem. So which means that it's repeatable in the sense that I don't want to solve only a single problem, but I have a whole so the problem itself is stated in a very broad terms, and you have some solution mechanism which you can apply multiple times in different contexts. And from where come these patterns? Astonishingly, it doesn't originate from the software world, but it was invented by this groundbreaking book. It's called A Pattern Language. It was written in the 1970s by an architect named Christopher Alexander and his team. And they put up some common patterns like in the realm of architecture, of building towns, constructions. For example, they had a pattern which is called neighborhood boundaries, how you should model the boundaries to your neighbor so that you have a good neighborhood thing, or even some sort of like ceiling height variety to say that different rooms have to have different heights in the ceiling to make it more comfortable and more nicer. So these are sort of patterns. They are connected to each other. And one common characteristic is that each pattern has a name and they form some sort of language, which means that the idea of this pattern language is that if everybody has read the book and knows the name, that as soon as somebody talks about this pattern, you only have to mention the name and the same mental picture somehow appears in everyone. So this is the idea of any language, by the way. If you talk about tables, for example, everybody of us has some sort of idea what a table is. Okay, this was from architecture. And then maybe, I think, 15, 20 years later, this concept emerged to the software industry, and probably this book, probably everybody knows who made up his career in the IT branch, in the IT world. It's the famous book of the Gang of Four, which is design pattern, which define patterns like singleton, like factory, like strategy, delegation pattern, and so on. Now this is as I said, a very famous book, and we all probably know at least the concept, even if we don't have read the book, but we know the concept which has been laid out in this book. And a lot of other areas in the field of software technology has also picked up this pattern concept. For example, there are books about enterprise integration patterns, how you should model your enterprise integrations and so on. But now I want to stop here. It's not a talk about the pattern theory behind this all, so I take a very pragmatic approach for this talk, where my patterns are really defined, each pattern get a name, I describe briefly the problem, and then one or more patterns with a solution, and at the end there's always a brief discussion about the pros and cons of each of these patterns. If you want to know more about how you, for example, how you can write patterns, there's a nice article by Martin Fowler, because there's no real standard how patterns are really described. Everybody does it differently. And you can look it up. It's quite nice to read. Okay, so now to the meat, let's say it like this. The first area I want to touch is configuration. So if you have your application, if you want to put it into your Docker containers, and of course you have some sort of configuration, you can put part of the configuration within the container, but then of course you want to move your Docker image to different stages. For example, you want to have it in the development stage where you connect to external services specific to your development environment, but then you move on and go to testing and production, and then you have a different set of configurations. And the big question is how you can configure containerized application that they fit for different environments. Here. There are several possibilities. I've selected 3 of them and want to explain them a little bit in more details. Of course, the easiest way to do this via environment variables. This is the usual way which we know from Docker, and also, by the way, who knows the 12-factor app thingy? Okay, maybe 1/3. So the 12-factor app manifesto, I think it's called, is a set of 12 rules which describe how you, or best practices, how to write stateless applications. And one of this, in chapter 3, it defines that every configuration which differs from context to context should be put into environment variables. Why do they say so? It's one reason is that it's a standard method which is known very well over a very, very long time. And you have a universal support from each system. So you have a universal support for defining environment variables in each of these platforms, but also for getting the variables into your applications. And for Docker, you can define environment variables in 2 ways, at 2 points in time. One is during build time, when you create your Docker. There you can define environment variables, but you can define them as well during runtime when you start your containers. So here's an example how it looks like. So in the upper here is a Docker file part where you simply have an env keyword, and you provide the keyword, the environment variable name, and provide some sort of value. And then you can override this value during runtime when you create a container out of your image. And you can override existing environment variables, but you also can of course invent new environment variables, and then your container which has started has access to all of these environment variables. So this is probably nothing new, so if you use Docker, this is a very common way to do things. It's a little bit different now if you now go a little bit further and for example look at Kubernetes. As I said, Kubernetes is an orchestration platform for Docker containers, which allows you easily to distribute containers over multiple nodes and hosts, and Kubernetes is the API server which simply checks that is responsible for scheduling all these containers on the different nodes, is responsible for checking that each application is still running, and just in case it's not, then it's restart the application again, and so forth. And Kubernetes concepts are based around so-called resources. And these resources are described with very lengthy resource descriptors, which are YAML files typically. And one of these parts, so maybe it's not so easily readable, but here you have some sort of environment stuff. You can provide also environment with name and value for the environment variables. And then you have some sort of extensions where you can have some extra interaction where these environment variables come from. And one of this is, for example, so-called config map and secrets. So it's a Kubernetes concept for putting some sort of key value pairs into Kubernetes itself. But as you can see, the point here is to say that Kubernetes, of course, supports environment variables as well as Docker Compose does. So it's the same here. You have a Docker Compose file. Docker Compose is also some sort of mini orchestration framework for starting up multiple Docker containers on a single host. And here you can also provide environments. You can even leave some environment values empty, which means that you have to provide it during startup. Okay, this was some sort of interest. So the question is now, what are the advantages and disadvantages of having configuration purely only with environment variables? The good thing, of course, as I just told you, it's supported everywhere. It's very simple, it's very explicit. So if you read this, you really understand what is going on. One of the, but then we also have problems. The reason is if you have many configuration variables which differ from environment to environment, of course you have to maintain many environment variables, and this can get quite a burden. So it's hard to maintain. It's also hard to maintain because you have different places where you can specify environment variables, and you always have to look for where the real definition is. So you have things where you can override environment variables, and so sometimes it's quite a hunt to find the real definition. And the other point is that it's static in the sense that if you have started your container, you cannot change the environment variable anymore. This is typical for any Unix process. So if you start a Unix process and here's some environment, if you change the environment variable afterwards, it doesn't matter for the process. So this is one of the drawbacks. What can we do? So there are some other ideas, now a little bit a more involved concept. It's called configuration container. And the idea is that we put all the configuration which we need for a specific environment in a dedicated container. And we bring together the application and this configuration container together during runtime. This is also an example of a so-called SIDECAR container, which I'll explain later on. So here's an example. What I have here is a Docker file. This has a base image called Scratch. Scratch is the smallest base image available in Docker, which is an empty image, so you don't have any operating system more or less there. And then you can add some stuff into this image under a certain path. You export it as a volume. Then you have this image. You create the image with Docker build. And after this, you need to create a container out of this image. This you can do with Docker create. In this case, after this step, you have a container config called config dev. And finally, when you start up your application, which we have here is, for example, here a Tomcat, you simply say, take all volumes exported from this container and mount it into the same image. And so you can see, okay, maybe we just do some sort of, oops, sorry, next one. Short, quick example. Sorry, I have to go down on it. So what you see here is, I have here a simple Java application. Oops, sorry. Oh, come on. Okay, this is a very simple application. So what you see here, it's a HTTP servlet. It has a simple get method. It does nothing else than writing out a simple dump HTML page. And it gets its configuration, as you see, properties from a file input, which is found here under a fixed path. It's called config demo.properties. And there we have two values which we evaluate. It's the color and it's the label. Then I have here two different kind of properties. One is the dev properties, which is simply done, used now in development. You have some, can make it a little bit bigger, I hope so, no. Okay, which is read in development, and you have the same, of course, if you go for the prod properties. The same now in green in production. Okay, this is now our ingredients. Now I have a Docker file for my application itself. This is a plain, as I said, it's a web application. I have already built it with Maven, so I have a demo.war here. And I use Tomcat as a base image and put it directly into the Tomcat Web Apps directory where it gets deployed automatically during startup. Okay, I can create this image. So docker build -t config container dot for the context. So hope so that it works. No, takes a bit. Oh, come on. Slow is slow. Come on. The demo gods are not with me. I think I'm in Greek there. All these Greek god could help me here, but the demo god is not among them. Okay. Just start again. Oops, sorry. Okay, so now let's, as I said, I already have, of course, tried this already. So I have an image which is called config container. Okay, but this is not the point. I have now my application in an image called config container. And now I just want to look in the other Docker file, which is Docker file config. And what you see here now is that you have here, again, the Scratch directory base image. Here's some feature called from Docker, it's called build arcs, which you can fill in during startup. And then we simply add this configuration under this very path, which I have shown you in this servlet. So this is then exactly in this path, and I'm exporting this directory here. And now I'm just trying, so I hope that my Docker build -t config dev image -build arc. So I just put in this dev properties for the case, and of course I could do the same for the production file. And I have to provide the Docker file config thing, and I build it here now. Also, of course, build arc needs this in the key value format. Okay, so I have now an image called config dev image, and now I can create a container out of this. With Docker create, I have to give it a name. So I call it dev config. And I have to say from which container I want it to have. It's dev config. No, I think I call it config dev. Do it otherwise around. Config dev image. So I have now created a container. This container is not running. So it's simply a dead container. So there's no process in it. It's simply just a container. And the next step is now I can call docker run -it. I want to export port 8080. And I say I want to have all volumes given from this config dev thing. And to start is my config container. Config container is simply the name of the example I'm using here. So what you see now that the Tomcat is starting up. And if I go now to the real side here, you see that it's really big red and thing. And the good thing is that if I do the same for the product thing, so I already have created this config prod container. So I only have to exchange this during runtime, during startup, the other container. Config prop, no, I have to create it, sorry. But I already so now let's start. Okay, now you see it's running in production. So where's my pointer? Okay. So, sorry, I have to go to the pro and contras. Okay, what are the advantages of this approach? So the advantage is that it's very flexible, it's still explicit, so you have your containers available there. And the good thing is that you simply could put your containers also under version control, of course, because you simply can push it to some registry, the images which are used for creating these containers. And so you can have some text on them, you have some version on them, and you can really version your configuration, which, by the way, can be much, much more complex than the simple properties file. It can be a whole set of configuration files, and you can put it into it. The disadvantage is, again, that it's always brought together during startup, so you cannot change it during runtime. You have, of course, you have seen I have to type a lot of things. Of course, you can script this as well, but it's a lot of it's overhead. It's more overhead than using plain environment variables. And of course, you have to agree on some sort of custom file layout. So this is the point of this config container thing. The third part in this area, now we come to a configuration service. So a configuration service is simply a service which you use to, where you look up your configuration actively from your application. So you use some sort of a configuration store. There are several available. There are so-called key value stores, which you can use, of course. Zookeeper is very prominent. Other ones are Consul from HashiCorp or etcd, which is a very lightweight key value store, or Redis, or anything which you can use for storing configuration. And then you simply access from your application to this configuration service. So I have a demo here, but I would like to skip this one. Maybe, let's do it. Let's try it. So I have here config container. So in this example, I have a Consul as a service. I just, oops, sorry. No. So what I do here, I'm running a already given key value store. So Consul itself comes also as a Docker image, so you can start it easily. You give them some options. You export a port 8500 to us so that we can manage it. We just started. And then I have also now my application itself. It changed a little bit. This was the same as before. So here in this get properties files, you see that I'm using here now a really proprietary API for accessing this Consul service. And then I get some values from the store and give it out and I can change the things. And again, I have here I started here. So what I have to do is to link this Consul image, which I just have started above, to my container, start the service. For this already. So as you can see, I've already still my last demo is still running. This was Consul. Don't have to kill my. Okay. No. Docker stop F3. Oh no. Okay. I think this is not. Okay, now it started. Oops. Just try it again. No, or the wrong one. Still have one. This is probably Docker. Let me say, this one here. Docker stop 1 F1. We try. Okay, now the service started. If I go now make here a reload, you will see that I get a null pointer exception, of course, because I haven't yet defined this interface. But what I can do is to go to the UI. This is the UI from Consul. As I said, it's a key value store from HashiCorp, which already comes with some thing. I can create here some sort of labels. So I say here, Voxxed Athens, create this, create another one, which is color. Let's call it blue. Create. And then we go back to the Tomcat, make a reload. And what you see is now it's blue and in green. Thanks. So the point here is, as you have seen, I can change it also after the container has started. So this is really the advantage of, the advantage of this approach, that it's dynamic, that it's flexible. Of course, the drawback is that you introduce some sort of external service, and so you introduce also some sort of latency. It's probably not really worth there because it goes quite fast. But you have still a maintenance overhead because you have now to start up your console daemon. And another point is that whereas it's an advantage that it's dynamically, it also weakens the sort of immutability so that you not really can be sure at any point in time what state your system has with respect to configuration. This can be also a drawback. Okay, now you have seen several ways how to configure stuff. Now let's go on and check for how service discovery works. So what do I mean with service discovery? The idea is, so we are now living in a microservices world, and you know if a service is micro, then there are many of them. And these services need to discover each other, and the question is how they can do this. Yeah, and this term is called service discovery. And there are also three ways which I want to explain you. One is, again, this thing with environment variables where you inject services via environment variables. Again, they must be set during startup. An example for this environment variable injection pattern is Docker links and Docker network. This means if you start up your containers and you link them together, as I did with this Tomcat stuff in the previous example, then certain environment variables are already set by Docker. And you can easily benefit from them by simply evaluating them in your application. The same thing works with Kubernetes and also Docker Compose. And for example, for Docker, it means these environment variables have always the same scheme. So first of all, it's the name of the container who exports the port. Then you have the port number itself, and then for each port which is exported, you have the address. This is the IP address. Then you have the port, and then you have the protocol. And this is also available when the pod starts. We can have a brief look now in our container, which is already running. No, sorry. It was too fast. So this is already running here. I am still running my Tomcat container config service. I jump now into this container. So I need the idea is cm1f. I make a bash. So what I do here now is I jump into the running container which is running. If I spell it right, then it's okay. And what I can now check, if I check the environment variable within this container, you see that there are a lot of environment variables set automatically. And these come from this console service which has been linked together during runtime. Okay, what are the advantages of this approach? Again, it's simple. You don't need any lookup. You get some things injected. The environment variables are set for you. Again, the problem is that you only see services which already exist when you start. And this is really a big problem because, you know, in such a world, microservices, orchestration things can come and go at any time. And if you use environment variables like this, you implicitly expose a startup order. So you require that all your services start before your applications start. And this is not something which is very suitable in a dynamic world. Therefore, you could do something different. One way is service lookup, and you see it's quite similar to this environment configuration thing, so there are similar techniques. One is, again, you store your key value, your services in the key value stores, and there are nice things like this glider labs registrator, which you can reuse on your own. This works like this, that it's also a container which starts, then it connects to the Docker daemon, it watches on any event happening there, and if another container starts, it simply takes this information and registers it at some sort of backend, console, etc, Sky DNS, and then your application can simply look up into this backend for these service parameters. With registering services, I mean service IP address, the port, and the protocol. So this is something if you do it on your own, but of course if you use something like, no, this is something you can do on your own. It's good, it's explicit, it's dynamic, so if a service comes and goes, the backend store will be updated, and you need the support from the platform, and you also, of course, you log into the vendor, into the key value store you are using. Therefore, is now the third part, which is actually the most used part and the most recommended part in most use cases, which simply uses dynamic DNS for service discovery. We all know DNS for resolving IP addresses and or resolving names to IP addresses, and you have certain kind of records in your DNS names, domain name service. And one special record is a so-called SRE record, which contains all the IP address for a name, but also the port numbers and some sort of priority stuff. And again here, for dynamic DNS, it works similar to the service lookup I showed you previously, that some piece of software registers the services at some sort of backend thing, like console or SkyDNS, and then your query for the service itself is not done via a proprietary service API, but simply via DNS. You simply query via DNS your service, and this can be done with standard means. You can simply use JNDI for this stuff, but if you use JNDI, it looks as ugly as this. Yeah, you need to have some sort of JNDI, DNS, context factory, and so on. And at the end, you get some sort of single plain text line, which you even have to pass further. Here you see the port number, and here you see the name for the service, which you then simply can contact using an URL. If you want to have it more easier, you simply use a custom library like Spotify, DNS-JAVA, which you can use, and this already gives you the information already passed nicely and in a typed fashion. And of course, if you know the port, so this is all done only to get to the port of the service. If you already know the port, for example, that your MySQL is always on 361 or something like that, then you can simply use the name of the service or the container as a host name to contact to the other stuff. So this is quite easy. So you don't even have to make an active DNS lookup. You can simply use this. So it's very, very convenient. And actually, it is very good infrastructure support. You can debug it with the usual DNS debugging tools. And yeah, it's a standard, it's dynamic. It unfortunately has also some sort of deep interaction with the operating systems. This means if there are some issues, you have to dive really, really deep until to understand it, because there can be many places where things can go wrong. Yeah, and this is more personal thing. It feels a little bit rusty, but nevertheless, it doesn't mean. So I'm also an older guy, so it's not really a disadvantage. So yeah, who does support dynamic DNS? DNS lookup, Kubernetes does it, Docker Compose does it, Docker itself does it. So every current platform nowadays uses DNS mostly for service discovery. So these are the three parts, and at the end you can say service discovery via DNS is the first choice, but if you wanted to have more simpler or you have a very controlled environment, using environment variables could be even easier. Now to the third area, it's a sidecar. This is a more general pattern, which is quite interesting, but you probably already heard about sidecars. And the idea is, or the question is, the problem, how can I decouple functionality for a container without even touching the application itself? What do I mean? So I have here the three patterns, which I show you in a second. So a sidecar combines multiple containers to a functional unit. Docker itself only has the container as the basic object, whereas other platforms, for example, Kubernetes, has the concept of a so-called pod. A pod is nearly the same as a container, but it can contain one or more containers, which are linked together and which live and die together. So it's really the basic block in Kubernetes is a pod. And so you can put in a pod, you can put your application in the container, and you can put a so-called aspect in another container, and they can talk with each other. The good thing is that you can separate the concerns, and one of the examples I show you on the next slide is, for example, if you have your main application is a Node.js based application maybe, and you serve some data, and you have your JavaScript files also in this main container, and they are stored on disk. Now what you want to have is now that things get updated immediately if, for example, something changes on GitHub or on Git. what you could do, of course, you can extend your application itself to say, okay, I'm looking on GitHub for polling it from time to time and making an update on the disk. But the other and more elegant way is to say I have a separate container which is only there for doing this synchronization. So for either polling for Git or listening on a webhook, and then update the data on the disk, which then automatically by hot reloading is taken up by the application itself. And so it's a feature, so you can even say without touching your application, you can say, oh, I don't want this synchronization stuff, I simply drop this container there and your application still works the same. So you're very, very flexible during runtime. And this is the general concept, and there are two sub-patterns from the sidecar. One is called embedder, sorry, the typo, or also called proxy. And the idea here is that this is for outgoing traffic. So your application, for example, has to talk against the database. But you don't want to couple it directly with the database because maybe your database changes from environment to environment, maybe not the type, but maybe some sort of version or some extra configuration. And what it does, your application then simply connects always to localhost to a certain port, and on this port is listening another container, which simply proxies to the real system in the backend. So if you look at graphically, for example, here's an example with memcached. You have a Python container, and when he's trying to look up some stuff, it contacts to localhost, a certain port, and on this port listening is another container which then does the real work. So also a nice way to decouple things for outgoing traffic. And the opposite pattern for this is a so-called adapter pattern, which does it exactly vice versa, which is there for standardizing and normalizing output. This good example, for example, is monitoring. Your application exposes some sort of metrics to the outside, and you want to monitor it, and want maybe to store it in some sort of central monitoring system like Prometheus. But each application does expose the metrics differently. Java does it differently as a C# application, does it differently than a Python application, and so on. And so you could adapt your applications always so that it exposes Prometheus, the metrics in a format that Prometheus expects. But you can also do it differently to say, okay, my application is left untouched, and I simply put in another sidecar, so in this case an adapter, which simply exposes, in that case, for example, is the metrics information is stored on disk, and the monitoring information exposes with a standardized format to the outside. Again, the benefit is that you decouple these functionality, which are more or less, one is an infrastructural feature, where the other is the business feature. And in principle, of course, you can easily exchange these adapter and so introduce a new monitoring system without letting the application itself know. So this is a very pragmatic thing. And the advantage of these patterns, of course, that they're the decoupled things that you separate of concern. Of course, they are more complex, but you will see more and more of these patterns in the wild. For example, things like circuit breakers or tracing, which currently mostly done within the application itself via the Netflix stack, like with Hystrix and so on, or Zipkin. These will move out to the platform because it's an infrastructural aspect. So your application does not need to know how to decouple services and so forth. And so the idea is to put this more really into sidecar containers, which does the decoupling, for example, for a circuit breaker in a sidecar container, not in the application itself. The application simply connects, and of course, the sidecar container needs to know what to provide in case of a failure or so. But this is the idea, that infrastructural aspects go out of the application itself and go into such sidecar containers. Okay, now to the last area which I want to show you. It's all about image building, so how you can create Docker images. In that case, in this example, specific for Java EE applications. You know that Java EE, of course, is a little bit, people might not like to put them in the container, but they have some certain advantages that you still code with Java EE in the containers, and I will show you hopefully what kind of advantages you can expect from Java EE applications in Docker images. And here I want to show you two patterns, which is how you can cut your images to conform for this Java EE use case. The first one is a so-called self-contained application, which means that this is the example which I have shown you previously. You simply have a base image, and you put your application on top of this base image, and then commit it, and then you have your application. So this is quite simple. You have one image you have a server base image, and then you start it. The issue here with this approach is, no, not the issue, but the advantage is you have a single deployment unit, you have a single image, it's easy to understand, it's easy to push somewhere and to start it. The problem actually is that you have a coupled life cycle with the base image. So, for example, if your base image changes, you have to recreate your whole image. So, and since typically the base image is built and maintained by a different team than the application itself, you need some sort of process for getting this done. You need some sort of communication, you need to get notified if the base image changed because of some sort of security fix, you need to recreate your application itself. So you have a coupled life cycle. This might be or might be not a problem, but to avoid this, you can use a so-called artifact container. And this is the same principle which I've shown you with this config container thing, where you say you put your artifact in a dump container, which has no action, it's simply only the data, and you have your application server, your Tomcat or whatever, and you bring them together during runtime by linking them. So you always, and then when the Java EE server starts up, it automatically deploys this artifact. And the advantage, of course, is that you have independent life cycles. So your application, your application server image can change independently from your application itself. The only thing which you need to adapt, of course, is the startup. So you only have, it might be only to a new startup of your application, so you have to update the link between both, and so it's easier for having independent teams. Of course, the drawback is now that you have to manage, again, 2 images. And yeah, so the basic thing why Java EE server still plays a role in this Docker world is that you have a lot of infrastructure code within the Java EE server, which your application does not provide. This is the whole idea of Java EE. And so your Java EE files, WAR files, are typically very, very small. So you have a WAR file, you can have as small as 50 kilobyte or less if you use all the Java EE provided features. And doing so your application image is, or even if you are using the self-contained thing, your layer where your application resides is very small, so that the rebuilds are very, very fast. So your development cycle is very, very fast. Whereas, for example, when you're using Spring Boot or Wildfire Swarm, where you have this sort of fat jar and you put everything into a single jar and you have to rebuild this jar and you have to rebuild your Docker image every time, then you have very long Docker turnaround times. It's not only turnaround time for building, it's all turnaround time for deploying, for pushing to a registry and so forth, because the layers get much, much faster. So in a certain, so there are even people who say this is the preferred way to create Java applications for Docker containers are with Java EE servers. So, but your mileage may vary. Okay, so I'm close to the end. So I have one last pattern, which is the idea about how to build Docker images. Actually, I have a whole talk about this one, which is with 10 different kind of patterns. I only want to show you, actually, I want to mention 2 and want to show you 1 maybe. So one thing is, in general, you can do it in 2 ways. Either you put the generation of your Docker images directly in your Java build process, which means you put it into your POM XML or in your Gradle build file, for example. The other way, of course, is that you don't do this, but you generate your artifacts as usual, and then create the Docker image through a CI system like Jenkins, where you create the images and push them to some registry. I will show you this build-in integration. So both have their values, but I will show you quickly how this build integration works. So in this case, you put the creation of the Docker image directly in the build, and there's one Maven plugin which is currently maintained. It's the Fabricate Docker Maven plugin, which you can use. This comes from our team. And the benefit of having this is that you can easily reuse information which you have in your POM XML anyway. So you can, in this case, you see here a configuration of this plugin where you define an image. You can define multiple images, but this is one. You have 2 aspects, build and run. And in the build part, you can define base image and other stuff. You can use an assembly descriptor, like the Maven assembly descriptor, the Maven assembly descriptor format. And in the run part, you can define how you can start this image when you start it. I will show you this in a second. And here the nice thing is you can easily map ports randomly to a random number, and then put this random number into some sort of Maven property. And this Maven property, which then is set, you can then reuse this through an integration test. So the whole idea to start Docker containers from within Maven is to have it, let's see whether it works for the last demo. So if I have prepared it here, and this is a simple example which start up a database, a prefix PostgreSQL database. I have an application which writes in its database, and this database is started during the beginning of the integration test. Of course, in that part, it's simply building the image, which you see here. So I have here a Maven sample image, and then you start the database. This is Postgres. The plugin then waits until a certain line appears in the log file, and after that, it starts a Tomcat. This connects to the database, and then you have your system set up, and then you run your integration test against this application, and at the end, you simply tear down everything. So you have a full self-contained integration test in your POM XML. You don't need any CI system for that. And the good thing is, of course, you can run many of them in parallel because they always choose random ports and you don't have any port conditions, which is a nice thing to avoid flaky tests, for example, on configuration system. Okay, I'm close to the end. So here, again, the advantage is self-contained. You can simply give someone the POM XML and he can run all the tests themselves. Disadvantage is that it has maybe a own configuration syntax, but you can also use plain Docker files, by the way, with this plugin. So you don't have to use this XML syntax, you can use it plainly. Okay, this bonus stuff is just one note. It's called a wormhole pattern, which shows you how you can run a Docker, like I did in these examples, how you can access the Docker daemon, which has started the container itself. So you access the Docker daemon, which has started itself, so it's more a little bit, metaphysical. The only thing you have to do, you have to mount this Docker socket into the container itself, and then you can run Docker itself. So that's the reason why you could see this image there. The alternative version would be to use Docker and Docker. Okay, now I'm in the end to wrap up. I hope I could show you that patterns, which I shown you, like this configuration thing, service discovery, and so forth, can really help to use solutions not only for Docker alone, but also in systems which are based on Docker. We have touched several areas. And one of the most important patterns is the SIDECAR pattern, which you will, if you are working in the Docker field and other things, will meet from time to time. So that's it. If you're interested, just the last one is a marketing blog. No, just writing a book on Leanpub with my colleague William. It's very cheap, €3 or so, because it's very raw. And if you're interested, there are even more patterns which are on top of these work. Okay, that's it. So thank you.
Thank you very much, Roland. Okay. All right. I think we're kind of on time. We have a few minutes to spare. Let's take some questions from Roland while Elias Kotsos gets his presentation ready. Is Elias here? Is Elias here? Is he here? Can you load up your presentation while we take questions? And this is a good time to change rooms, but let's try and keep it quiet as we change rooms, so that we can hear each other. Right. Question. Shoot.
Why would you want to run a Docker container inside a Docker container?
So sorry, I couldn't hear you.
Why would you want to run?
Okay, the question is, we would hear the question if you guys were a little quieter. The question is, why would you run a Docker container in a Docker container?
The one reason for this presentation, which does it like this, for examples, but you have also things like if you have CI systems where you really start up the integration test like this, which you also, for example, Jenkins has some slaves which run in Docker containers, and then when you run the integration test within the slaves, you need to have some sort of Docker and Docker thing to accept this one.
Thank you very much. Question? One more question? Anybody? Raise your hand up high so I can see it. Okay, no more questions. Thank you very much. Thank you, Roland. Thanks. Thank you so much. So, Roland.